Yesterday, quite a bit was spoken about performance of materials and design, structural design and structural considerations. What I'd like to talk about now is another very important component, and that is how does one provide the best composition of a mix or an appropriate composition of the mix to give you the performance that you're looking for. And it is just as important as all the other steps when it comes to implementation of a technology for our road infrastructure. So if you don't follow a mix design, you're bound to have some nasty surprises. So if your objective is getting to the destination on your scooter and it doesn't happen, you haven't achieved your objective. So just like the mix design, we want to avoid nasty surprises. And some people don't learn from their mistakes. So in terms of understanding where we are now, it's useful to look at how we've got to this point. And on this graph, I've got time on the horizontal axis. And as you can see, we're only starting about 1990s with real work on mixed design of bituminous stabilized materials, whether emulsion or foam bitumen. On the vertical axis is our sort of reality check, reality index. So if we look at what has happened on the compaction front, this technology really started with Marshall compaction and 100 millimeter or 4-inch diameter specimens. Because of the generally quite large maximum aggregate size in these mixes, there has been a transition to 6-inch diameter specimens. And I should hasten to add that there's, in most places, at the same time, a recognized change in specifications, because whether you're testing a 4-inch or 6-inch specimen does make a difference to the performance properties that you measure. And then ultimately, there's been implementation over the last couple of years of vibrating hammer as a very useful compaction tool. Primarily, if we look at the history, FDR was, I would say, the real introduction of this technology, but more and more, as it's gained traction and people have recognized its reliability, there's been a transition towards using CIR and high percentages up to 100% of RAP. So one needs to consider the differences between these two technologies as well. The other area that has transitioned has been the evaluation tests. And what I'm talking about now is something generic that's being introduced. But as you can see over there, the technologies began with those 4-inch diameter specimens and evaluating the mix performance properties by the indicator test, as I would see it, or tests of the ITS and the UCS, the unconfined compressive strength. Those were useful, and they still have their place. They transitioned through the 6-inch diameter, but currently we've added another, and I say we, this is from a South African perspective, although it is being used in other countries as well, a triaxial as a closer performance-related test than the others, because it gives you more fundamental material properties in terms of shear parameters. And as you can see, what is currently being implemented, this vibratory hammer compaction, as well as triaxial testing and RTS testing, has now been used for a lot of different projects and mixed designs, and they're performing pretty well. Just a couple of details. The first step of a mixed design is to identify, do I have the right grading and the right types of aggregates to be able to do recycling with, to be able to bitumen stabilize. And sampling, as we all know, is a starting point. It was a very important point because this is where you can already begin to incorporate variability if it's not done properly. So one can go through that loop, and obviously if you don't have exactly the right grading you require, it is possible to blend, and this is a successful way of turning a sow's ear into a silk purse, if I can put it that way. You can improve the quality of the material just by blending the right components into it. Once you've got the right blend, the next step would be to evaluate the active filler, the effective active filler. And generally, depending on where the project is, one can consider lime and cement and other possibilities if they're available. We heard yesterday about fly ash as well. And one does performance tests to check which one works the best. And then one needs to use the same, this is all done at that stage by ITS tests because you've got a lot of variables that you're testing. And the same with optimizing the bitumen content, the binder content, part of the mix design. So there are different specification values used, and what I've provided there are the typical values that we have been using in Southern Africa and in parts of South America and other countries too. What sort of details are important about the material? Well, one needs to, if you're using bitumen stabilization, I mean, bitumen or asphalt cement is not a cheap material. So it's a little bit wasted if you try and use it on a material that's got quite a bit of plasticity. And in fact, we have become stricter on the plasticity limits. We were allowing up to 8% of PI, but found that it does compromise the performance of the mix. So it's become stricter. The 0.075 fraction, the 75 micron, which is called filler on that graph over there, one can see there are some differences between the requirements of foam and emulsion. Emulsion needing less of the 0.075 fraction. Important to get that right. And then if you've got 100% wrap, you can also relax that specification. As you can see, 2% passing the 0.075 is acceptable if you were doing CIR. When one's using CCPR, I think you call it, but the in-plant type of recycling, depending on how you are acquiring your wrap, and the grading that you've provided with, as well as the variability of the material, it can be really worthwhile to pre-process it through, for example, an impact crusher. It does certainly provide a consistent product, and that leads to more consistent performance. Just some practical aspects. I mean, for a project, if you're looking at a rehab project, the ideal would be to have a recycler to sample the wrap material that you're going to be doing your mix design on. But practically, this is not always possible because you don't find a recycling machine around every street corner, and it's quite expensive to get one on site. One might have a milling machine available, and just how the size of the milling machine, the configuration of the milling drum, as well as the speed of advance and the speed of the milling drum, these are all variables that are going to influence what grading of wrap you get out, and that's going to influence your mix design. So one needs to work with specifications or guidelines as to how to take these wrap samples. Because if you've got an unrepresentative mix to begin with, you're wasting your time with a mix design because it's going to give you the wrong results. Small milling machines, be careful, especially doing things like grinding, which is where you move very slowly with a small milling machine, and also, as I said, depending on the pick configuration, one can generate a very fine grading of wrap, which is unrepresentative. And on this next slide, I'll just give you an example of how much variability one can get depending on the way in which one, excuse me, the way in which one acquires the sample, takes it from the road. And as you can see over there, if you've got a cracked road and you use the wrong methods, particularly if you've got bad crocodile cracking, I think you've got alligators here, so you call it alligator cracking, but it's really the same thing. But one can get blocks coming out, and this obviously influences the grading, as you can see there on the grading curve. If one uses impact crushing or the right speed of milling, not grinding, one will get close to your representative sample, as you can see by the green line. And there are also machines that down mill instead of up mill that also helps to pulverize the material in the right way and give you a representative grading. So very important to consider what representative grading one can get from the wrap before you start doing your mix design. And there are ways of adjusting it. One can use little laboratory jaw crushers and this type of thing to give you the grading that you require. But it's quite useful, and there are published values like this, to get your wrap within an envelope before you go ahead with your mix design. As I mentioned a little earlier, one of the new introductions to the mix design system has been this vibrating hammer. It is not something completely new. Countries like New Zealand, Australia have been using it, but there hasn't really been specification values provided in those places. And as a result, there were different compaction frames, there were different weight and power rating of hammers, and this all influences the compaction that you achieve, which is something that you need to control and needs to be as representative as possible of what you're getting in the field. So this is now a commercial product that we see in the picture on the screen, and it's a certain specification of vibrating hammer and a given frame. We went through a lot of, let's say, teething pains in developing this system with different types of frames, with different types of hammers, and you can see the variability that one gets with different, just by changing the different frames and using the same hammers. So it's rather important to standardize this, otherwise one's not going to have uniformity in mix designs between different regions and different projects, etc., etc. I'll give you an example. One of the steps that we took in terms of the research was also just having a look at the tamping foot. And what we found was 0.5 kilograms, 500 grams, which is about a pound, difference in two different feet, tamping feet, could give you a 2% difference in compaction. So instead of having 100%, 98%. And this makes a huge difference to the performance of the material, and certainly the results you're going to get from testing will be significantly different. So that method has, particularly for FDR mixes, that it seems as though some CRR mixes with softer binder still obviously compact very well with gyratory, but for the vast majority of mixes, that vibrating hammer works brilliantly. In terms of curing the material then, the other thing is that one needs to do is understanding that this bitumen stabilized material, whether emulsion or foam bitumen as binder, needs time to gather strength as moisture is driven out after compaction in the road. And you can see a stiffness gain and strength gain for up to a year after construction. So we need to simulate this in the laboratory. And if we differentiate slightly now between ITS testing, and later on I'll just mention the triaxial tests. So what is quite widely implemented is curing at 40 degrees of the specimens that you've compacted in the oven. And that's done for 3 days to a dry, constant mass. So the moisture comes out. It's not representative of the final moisture in the road, but it's providing a benchmark at which one can do these tests. In addition to that, so one can test, and we call that an RTS dry if you test that specimen, but one can also make additional specimens and test them after 24 hours, a day underwater at 25 degrees. When one has these specimens, then you run through the process that I showed on that little flow chart. So the first step in that process would be to look at the mix design, and you have a typical binder content of bitumen, but with 1% cement or 1% lime, if you have the situation of having both those active fillers available, or whatever else you like, and also the addition of no active filler. And you run 3 repeats of each of those for dry, so that's why you see 3 of them in the dry state up above, and then 3 different mix designs in the wet state. So there's a whole bunch of tests right there, and then one will obviously cure those specimens and test them all at 25 degrees. Although it's stabilization, some people still need to get their head around the fact that temperature is an important consideration, an important variable when one's doing this testing. And we test at 25. Although the dry specimens come out the oven at 40 degrees, you need at least 4 hours to condition them to the right temperature. I've seen cases where they come out the oven, it's at 40 degrees, stands for half an hour, you use your infrared gun, test it, it's 25 degrees, I can carry out the test. Test it. When you open that specimen after you've done your RTS test, just check the temperature inside. You'll find it might be 37, 35 degrees, and you haven't tested the true RTS strength, and it really compromises the results. So temperature is very important. In terms of the active filler, one of the considerations, and it's often debated, how much active filler can you put into the mix? Well, this chart behind me, the diagram, just emphasizes the point that higher strength does not mean more flexibility and does not mean better performance. So the green curve as opposed to the red curve, it's clear on the vertical axis that you can see the strength of the material. It can be flexural strength, it can be tensile strength, but the strength goes up as you add more cement. This is as clear as falling off a bicycle. But is strength the only consideration? No. If one takes account of, let's say, a simple check like the area under the curve, giving us an idea of the dissipated energy in those 2 different mixes, more often than not, you'll find out that the 1% cement, the mix with 1% cement, actually has the more flexibility, and as a result, can accumulate more dissipated energy. So less is more when it comes to adding active filler in terms of performance, and one really needs to be aware of that. If RTS values are a little bit low, it's no good adding another % of cement to the mix just to get your RTS values right. Rather go and look at the grading, look at the important things to get the right mix design, because you want flexibility, and active filler, unfortunately, prevents the flexibility that you're looking for. How much bitumen do you add? So once you've gone through that step, now you've chosen, let's say, 1% cement. That works the best for my particular aggregate, and carry on with the mix design. Now you look at the binder content as a variable. And there are some guidelines on this, how much binder to add. You can see they're fairly small steps. But if one considers the cost of bitumen, and you're in a developing country, as where I come from, man, this can make a huge difference to the cost of the contract. The bitumen is the most important and most expensive material on the site. So it's important to get this step right and reliable results. So once again, one goes through this whole process, make all these specimens, do RTS tests, and then make a decision on which binder content will work. I was just talking in the break to someone about variability. This is somewhere that you really need to also account for variability. So what you see on that graph over there is on the vertical axis is your strength, your RTS strength, indirect tensile strength. And the blue one is for the dry RTS tests. And the horizontal axis is obviously the bitumen content that you've added. And the red line is the wet. And these are typically what happens. You usually get a parabola for the dry testing. It'll peak out at some point and then start to reduce as you add too much binder. Generally, the wet strength, the more binder you add, the more resistance to moisture you have. So it follows that sort of a trend, ever increasing. But how does one select the design binder content? Well, one can see there, between the two, now you've got a plot on the vertical axis, your specification values. Whatever they might be for your country, this is the principle of it. So in this one, the wet could get away with, well, I haven't taken account of variability there, but it could get away with a lower binder content, maybe 1.9% bitumen. But as you can see, taking account of variability with the dry specification, one would probably need about 2.1% bitumen to get the desired performance of the mix that you're looking for, according to the spec. So once one has passed through those tests, one knows what active filler to use, 1% cement, for example, and then you've got 2.1% as your binder. That is then your design mix that you're just going to test the shear properties for. Once you've reduced the variables, then one can go on to triaxial testing, because just one specimen weighs 12 kilograms. What's that, about 25 pounds or something like that? So it takes quite a bit of material to do a mix design. And with that one composition, one continues with the triaxial testing, which I'll explain briefly. So firstly, one has to go and compact the specimens. Again, one can use that vibrating hammer. We set it, as you can see over there, 5 layers for 12 inches. So that's 2 inches per layer. And, no, is that right? 6, it's a bit more. 5 layers, so it's 60 millimeters. Yeah, it's, what's it, 1.25 inches or something like that? 2. No, it's not 1.25 inches. It's 2 and 3/8. Thank you. I don't work in imperial very much anymore. So at 60 mils per layer, you would compact it to a constant height. So you're setting it at a certain density. And that vibrating hammer machine with the frame, you can set the height setting so that it compacts until it reaches the desired height, and the machine automatically switches off. You then have to scarify the material, and that's that thing over there. It's a highly sophisticated device, as you can see. But the nice thing about that, we used some crazy methods to do it, and it was so variable. That device gives us just so much roughening, and then you can add the next layer and you get a good bond. So it's actually a very useful bit of equipment. Curing of the specimens, a little bit different to the RTS. Still 40 degrees, but here we keep it in the mold for 24 hours. So this allows, you've got to have enough molds for the mix design. That's important. It allows the material to strengthen before you take it out the mold. Then you need 8 hours. What we're trying to do here with the RTS test is simulate the moisture conditions in the road once it's cured and reach some sort of an equilibrium moisture content. And then you seal it, and so that you don't lose any more moisture, and then a further 2 days in the oven. So it typically works out at about 3 days anyway, before one does the testing. The soaking is very similar to the RTS. So it's 24 hours at 25 degrees. One would make 10 of those specimens. So you compact 10 of those specimens that we're going to use in the mix design. 8 of the 10 specimens you will use to get you to plot your Moore-Coulomb circles. And you would test them at different confining pressures, as you can see. And then the other two, you would only use one confining pressure, but this is to test the moisture exposure. And what I've added there is, and this helps in terms of getting a consistent mix design and reliable parameters. And that's just a simple t-test, statistical test, to check if any of the densities of your specimens are outliers. You can always recompact another specimen. Now's the time to do it before you go and test it. So that's a really useful way of ensuring that you've got a reliable mix design. How do we test it? Triaxial sounds highly sophisticated. What we developed just in our research laboratory, and it's also now rolled out into a commercial product, nothing to do with our university. This is it comes from Germany, this product, but it's got a sealed tube, and that's what you can see over there. So there's your compacted specimen put on a base plate. You've got a sealed tube with a valve where you can inflate the tube, and just a confining cylinder to go around it. So what you would do is place your specimen there, put the tube around it, and then place the confining cylinder over that, and then put a base plate on top. Apply with an air regulator, just apply air pressure that inflates the tube and gives you whatever confinement you require. So it's a very quick type of test to do, but it gives us our more Coulomb plots, so we can get a really accurate measure of cohesion and friction angle. So why is this so important? Well, as I mentioned yesterday, the shear parameters are really a strong link to the performance of this material. So we've seen that from research into just the granular material, and once you bitumen stabilize it, what you can see is, as was shown in the animation, it really, with a foam or emulsion, what it really does to that mix is it gives it a kick in the cohesion. But the friction angle, because you've got individually dispersed bitumen particles, it doesn't really lose friction angle. So you might have a slight change in the friction angle, but not very high. So what we get from the testing, you would have two more circles at 0 confinement, 2 at 50 kPa, 2 at 100, so one would go and plot those, and 2 at 200. These are all of those equilibrium cured specimens, and from that we would be able to plot our failure envelope. Very useful now. We've got the parameters that we need and feed it into the structural design, and reliable parameters, but we can also check whether this mix complies with the specification requirements, which are 250 kPa at least cohesion and a 40-degree friction angle. Those last two specimens are then used to check out what is this mix's resistance to moisture like. Is it good enough? And we allow for a maximum of 25% reduction in cohesion. So that is what we test over there from those two specimens. Again, you can check that out in the specifications. This is what a typical plot looks like. And one thing I'd just like to emphasize, these are actual results. It's not unusual to get R-squared values for your 8 specimens that you've tested above 0.9 and typically above also 0.94. So in summary, Mr. Chairman, what are the benefits of this mix design? Because at the end of the day, one doesn't necessarily want to undertake more sophisticated testing, although this is not highly sophisticated. What are the benefits of these new mix design procedures? Well, one thing we've done in terms of those pictures over there, we've done CT scans and looked at the packing of the material. What we're finding is with that vibratory hammer compaction, we're getting much closer simulation to a representative compaction of the layer in the field. In the bottom, we can see over there, I've already mentioned the link to pavement design. a more accurate simulation also with the triaxial testing of the moisture damage. So this is very important, and because it influences our deviator stress ratio, and that's going to influence the life of the material. Identifying the true behavior of the material. This is just an example. We did a mixed design on a project that had bitumen rubber asphalt, was recycled. Up to the RTS testing, the results looked pretty good. What enlightened us to the fact that things weren't so great was when we did the triaxial tests on that material. So we found that we weren't getting the desired compaction and we weren't getting the performance properties, and some changes had to be made to the mixed design. So the RTS test provided what seemed to be good results, but the triaxial test alerted us to the future problems we were going to have with the performance. Another example was a job I had some involvement in the Middle East, where they used bitumen stabilization, and it was wrap, and it was with soft binder in it. And this led to some, because too much added bitumen was added when the foam was applied, resulted in too much binder in the mix and permanent deformation. When we did the triaxial tests, you can see we took temperature into account, because in this place, it was not uncommon to have temperatures in the road, in your thick layer, of over 50 degrees. And as one can see, this has 40, 50, 60, has an influence on that failure envelope. So we had to, as part of the rehab measure and improvement of that project, blend the mix, because it had soft, high binder content, because I mean bitumen in some of those countries is just about for free. I think it's cheaper than water. So there was too much binder in the mix. We had to blend some virgin aggregate to get the desired shear properties in the material. And we could see this through the type of testing. I've emphasized, hopefully, the importance of repeatability and reproducibility in the tests, and this system is helping us to control that. It's also helped us in investigation of some projects where too much cement was put in. One can pick it up very quickly also with very high cohesion values. It also comes up in the RTS. And then that dissipated energy consideration, our research has shown what are the key variables we need to consider. Confinement, moisture is another one. Confinement also is enhanced through compaction, so you can, in your layer, create more confinement by getting a better compaction. And in order to do that, one thing that's necessary is having the right grading, so you have the right packing. So to end off with, I'd just like to highlight again how important the investigation is and the sampling of the material. We've got this equipment, it needs to be properly used, and that's why there are protocols that need to be followed. For QC, I didn't mention that, but for QC on the project site, we still only use RTS tests. The triaxial only comes in at the mix design for refining the mix design. Very important. And then the benefits, hopefully, from those last couple of slides, you can see some of the benefits of getting measures of the cohesion and friction angle, and gives us also more reliable structural designs. So thanks for your attention, and I'll be happy to try and answer any questions.
Any questions for Tim? We're running a little late.
Yes, just one quick question.
Sure.
Your system is totally blind if it's virgin ground material to 100% wrap?
Yes, in principle, but no in terms of what you saw there. The controls on the percentage passing, the 0.075, the grading. For 100% wrap, you can have lower percentages of fines and filler down the lower end of the grading, and a few nuances like that. But it's aimed to be a blind of binder in terms of whether it's emulsion or foam, as well as FDR or CIR. I think in some extremes, there are some adaptations that are needed, and we're seeing that with some of the 100% wrap mixes, particularly if they've got soft binders. that one needs to take other considerations, because you start moving into, instead of being non-continuously bound, it's almost like a cold mix asphalt. And we see like gyratory compaction works very well for those mixes.